All right, let's jump right into this explainer and demystify API Specification 5L. If you've ever wondered how the massive arteries of the global oil and gas industry are actually manufactured, well, you are in the right place. This document is essentially the ultimate recipe book for manufacturing line pipe. It dictates exactly how steel has to be forged, shipped, and tested to safely transport high-pressure resources.
We have 5 clear chapters on the docket today: understanding API 5L basics, pipe grades and PSLs, the manufacturing process, chemical composition limits, and finally, tensile properties and strength.
Chapter 1. Understanding API 5L Basics.
Right off the bat, one of the first things you'll notice is that API 5L speaks 2 distinct mathematical languages: the International System of Units, or SI, and United States Customary Units, or USC. But here is the absolutely crucial point. While the spec uses both, you can never, ever combine them on the same inspection document or pipe marking sequence. If a purchaser specifies metric on their datasheet, everything has to be metric. It's a hard boundary, and it's there to prevent catastrophic measurement errors out in the field.
Now, the very foundation of API 5L is quality. Every single manufacturer must have a documented quality system applied to their production. But what's really interesting here is that the API doesn't strictly demand a third-party certification body to sign off on it. Instead, they defer to the expertise of the company's own quality management. So you can build your own system from scratch, or you can adopt existing, heavily audited frameworks like ISO 9001 or API Q1, which has specific provisions tailor-made for oil and gas.
Moving along to Chapter 2, Pipe Grades and PSLs. If you've ever dealt with ordering pipe, you will constantly see references to PSLs. This simply stands for Product Specification Levels. You can really just think of this as a dial that turns up the intensity of the engineering requirements. The specification gives us 2 settings, PSL1 and PSL2.
So PSL1, that's your standard everyday baseline for line pipe. It lays out acceptable manufacturing processes and standard delivery conditions. But when you crank that dial up to PSL2, you are entering a world of much stricter controls. PSL2 requires mandatory specific delivery conditions, like requiring the steel to be quenched and tempered, and it demands significantly tighter chemical tracking and testing across the board.
And when you decode the actual naming conventions printed on the pipe, those letters and numbers actually tell a story. For SI units, the letter L is followed by the minimum yield strength in megapascals. So L245 means exactly 245 megapascals. For USC, you get familiar terms like grade B or X60. But here's the kicker for PSL2. A mandatory suffix letter is added right at the end. An R means it's as rolled, while a Q explicitly states the steel was quenched and tempered. So just by glancing at the name, you know exactly how that metal was treated in the factory.
Chapter 3. The manufacturing process.
If you read through the specification, you'll immediately realize it is loaded with an alphabet soup of acronyms. Keep this cheat sheet handy. On the seamless side, SMLS is seamless pipe, meaning it's extruded from a solid billet with no weld seam at all. Then for welded pipes, you've got CW for continuous welded, HFW for high-frequency welded, SALL and SAHW for submerged arc welded, either straight down the line or in a helical spiral, and finally COW for combination welded.
Now, looking at the acceptable manufacturing processes laid out in the spec, you'll notice something striking about continuous welded, or CW pipe. Under the PSL2 requirements, it's completely gated off. It is totally forbidden for those higher-tier PSL2 pipes, regardless of the grade. The spec strictly gates the manufacturing processes based on the exact quality level you need for the job.
Furthermore, the spec doesn't just blindly trust that the machinery is turned on and working. Section 8.22 dictates very strict validation steps. Any operation that affects the final mechanical properties of the pipe must have its processes validated. Making seamless as-rolled pipe, you have to validate the final reheating practice and hot sizing. Doing submerged arc welding and expanding the pipe, you've got to validate the pipe forming, the seam welding, any repair welding, and the expansion process itself.
And speaking of expansion, it is a highly controlled mathematical process. For those making cold expanded pipe, the sizing ratio is strictly defined by this exact formula. You take the absolute value of the outside diameter after sizing minus the diameter before sizing and divide that by the diameter before sizing. The spec even sets exact limits on this ratio, proving that absolutely every single millimeter of deformation is accounted for and rigorously regulated. No guesswork allowed. Chapter 4. Chemical Composition Limits. You can think of this part of the spec as the nutritional label for your standard PSL1 pipe. It dictates the absolute maximum mass fractions of chemical elements allowed in the steel. We're talking strict limits for carbon, manganese, phosphorus, and sulfur. For instance, for a standard welded L245 pipe, your carbon maximum is typically capped at 0.26%. Keep that number in mind.
Because when you move over to the requirements for PSL2 pipe, things get significantly more complex. You see lower maximums for certain elements, sure, but more importantly, there is strict tracking of something called carbon equivalent. PSL2 requires this calculation to ensure the pipe can actually be safely welded out in the field without cracking under intense stress.
And this brings us to a massive, game-changing differentiator for PSL2. As stated in Section 9.2.4, if your product analysis shows a carbon mass fraction equal to or less than 0.12%, you are mandated to calculate the carbon equivalent using a very specific formula.
And here is that exact formula. You have to plug your chemical test results into this equation, factoring in the precise percentages of carbon, silicon, manganese, copper, nickel, chromium, molybdenum, vanadium, and boron. I know, it looks super intimidating, but this math is what guarantees the steel's hardness and weldability behavior. It ensures the pipeline won't suddenly turn brittle when a welder applies heat to it in a freezing trench in the dead of winter.
Finally, Chapter 5. Tensile Properties and Strength. This outlines the ultimate pass or fail test for these pipes. To meet the standard, a sample of the pipe body and the weld seam is physically pulled apart. The standard sets the absolute minimums for yield strength, which is the exact point where the steel permanently deforms, and tensile strength, which is the point where the steel literally snaps and breaks.
Notice how aggressively that minimum yield strength jumps as we step up the grades. Going from the baseline L175 up to L245 and all the way to a high-strength pipe like L485, it vaults from 175 megapascals to nearly 500 megapascals. The numbers in the names literally represent this incredible physical capability, which proves exactly why getting the chemistry and the manufacturing routes right from the very start is absolutely critical.
Which leaves us with a fascinating final thought to consider as we wrap up this explainer. If a single decimal point change in a carbon equivalent formula or a slight deviation in a hot rolling process can alter the entire grade and weldability of the steel, how much of our global infrastructure safety relies entirely on these microscopic metallurgical tolerances? Mastering this complex blueprint doesn't just make a pipe, it literally prevents macroscopic catastrophes. Thanks for joining me as we decoded API 5L. Keep asking questions, and I'll catch you in the next one.